Let us start chemistry. In chemistry, gaseous state chapter will start. In gaseous state, let us see Dalton's law of partial pressures. Dalton's law of partial pressures. We will see Dalton's law of partial pressures. In Dalton's law of partial pressures, we came to know that total pressure is equal to sum of the partial pressures. For that, let us take an example. Here we will take helium gas. We will take it is suppose x moles. It is x moles. It is V1 liter. It is V1 volume. Temperature is T1. And another gas we will take. Here we will take neon gas. It is some Y moles. It is V2 volume. Temperature. It is volume is same volume we have to take. Same volume we have to consider. Therefore V1. Temperature is same T1. It is here pressure exerted by helium. Here pressure exerted by neon. Next we will take. Here we will take argon gas. It is Z moles. We will take. Volume is V1, temperature is T1. It is argon is exerting pressure, that is called pressure exerted by argon. Next vessel we will take. Here helium is present. All the helium molecules will transfer into this vessel. All the neon molecules will transfer into this vessel. All the argon molecules will transfer into this vessel. So X moles of helium we transferred. Y moles of neon we transferred. Z moles of argon we transferred. This volume is how much means V1, temperature is how much means T1. Volume remains same in all the cases. Temperature remains same in all the cases. Now pressure exerted is by the mixture. Pressure exerted by the mixture. So now we will consider all these gases are ideal gases. We will consider helium, neon, argon are having ideal behavior. We will consider. Then we can write PV is equal to nRT. We can write PV is equal to nRT. Here this mixture is exerting pressure, that is called pressure exerted by the mixture into volume of the mixture is equal to number of moles of the mixture into RT. Like this we will write. Now PV is equal to nRT we have taken. In this P is called pressure exerted by the mixture. Pressure exerted by the mixture. Volume is called volume of the vessel. N is called the number of moles of the mixture into RT. Like this we have written. Then helium we will take. For helium we will write PV is equal to nRT we will write. Then pressure exerted by helium, volume of vessel. N is called number of moles of helium into RT. Like this we will take. This we will take as number 1. This we will take as number 2. Like this we will take. Next we will see 1 by 2 we will take. 1 divided by 2 we will take. So what we will get, we will see pressure exerted by helium equal to volume, number of moles of helium into RT. Then number 2 is what means pressure exerted by the mixture into volume of vessel by number of moles of the mixture into RT. What are the common terms will get cancelled, you see. So what is the rest? You see that pressure exerted by helium by pressure exerted by the mixture is equal to number of moles of helium by number of moles of mixture. Rest of the things are getting cancelled. Next step we can say pressure exerted by helium by pressure exerted by mixture. Pressure exerted by mixture is equal to what means mole fraction of helium. Mole fraction of helium. Number of moles of helium. It is number of moles of helium by total number of moles. This ratio is called a mole fraction. So it is called a mole fraction of helium. It is called a mole fraction of helium. So now we can say this is as a partial pressure of helium is equal to mole fraction of helium into total pressure. Total pressure. So we got what is the relation in the sense partial pressure. It is called partial pressure of helium, that is equal to mole fraction of helium into total pressure. Similarly, if we take neon, we can say partial pressure of neon is equal to mole fraction of neon into total pressure. For argon, if we say partial pressure of partial pressure of argon is equal to mole fraction of argon into total pressure. Like this we can say. Okay. So Dalton's law we discussed. In Dalton's law, two formulas. What are the two formulas in the sense? One is total pressure is equal to sum of the partial pressures. Another formula is partial pressure is equal to mole fraction into total pressure. Sir, okay. Next we will see effusion. Next we are seeing about effusion. Okay. What is called effusion in the sense? Suppose some gas is moving through a tiny hole. Moving through a tiny hole. Gas is moving through a tiny hole. That is called what means? Uh, this is tiny hole. Tiny hole. If gas comes out through tiny hole, then it is called a effusion. Effusion means gas is diffusing or gas is coming out through tiny hole. That is called a effusion. Next, called what means diffusion. Diffusion means diffusion. Diffusion is called intermixing of gases. Intermixing of gases is called diffusion. Intermixing of gases is called diffusion. Now let us consider two vessels. Two vessels we'll consider. In this vessel, let us take here one vessel we are taking. In this vessel, let us take some gas. Suppose we are taking helium gas. Helium gas in this vessel. It is closed like this. We will take another vessel. Another vessel we will take. We are taking another vessel. Let us take another vessel. We have taken another vessel. In this vessel, let us take some other gas. Suppose we have taken argon gas. Suppose argon gas we have taken. Now let us remove the partition. Let us remove this partition. Let us remove this partition. Okay. We will remove this partition now. Okay, partition is removed. Now what will happen? You say partition is removed. What will happen? What will happen to these two gases? Partition is removed. Before removing partition, how it is there? After removing partition, how it is there? Now, initially we have taken partition like this. We took helium gas here. Helium gas molecules are there. Here argon gas molecules are there. Here argon gas molecules, here helium gas molecules. If we remove this partition, what will happen? What will happen? Will the gas molecules intermix or they will not? What do you think? If you remove this partition, will they mix with each other? Will they mix with each other? What do you think? Will they mix or will not mix? This helium gas and the argon gas, will they mix or will not mix? What do you think? If you after removing this partition, shall we say helium gas and argon gas are intermixing? So, helium gas and argon gas are mixing with each other. While mixing in the sense, which gas will go towards which place? Will helium gas will move upward or argon gas will move downward? What will happen? Or both will happen? Whether helium gas moves up or argon gas moves down or both will happen. What do you think about it? Sorry, okay. Both will happen. That means helium gas makes a random motion. Argon gas also makes a random motion. Therefore, what happens means helium gas moving up as well as down, argon gas moving down as well as moving up, like this taking place, like this possible. So we can say that both gases intermix with each other. Intermix with each other if we remove this partition. After removing this partition, we can say that both gases are intermixing with each other. This process is called diffusion. So diffusion in the sense intermixing of gases. Intermixing of gases is called diffusion. Sir, okay. So we came to know that what is diffusion. We came to know that. Okay. Next, we will see that rate of diffusion. What is called a rate of diffusion? Rate of diffusion means what we will see. Rate of diffusion. Rate of diffusion. How do we define this rate of diffusion? Rate of diffusion, how to define that we will see. Now let us take another vessel. We will take another vessel. This vessel, in this vessel, let us take a gas. Let us take a helium gas in this vessel. This vessel is closed. That vessel is closed. Now let us take another vessel. We will take another vessel like this. We will take another vessel like this. In this vessel, we will take some gas. Suppose we are taking argon gas. Argon gas. Now, if we remove the partition, if we remove this partition, helium gas and argon gas will mix with each other. Helium gas and argon gas molecules will mix with each other. Helium gas molecules and argon gas molecules are mixing with each other. Sir, okay. Now let us consider 1 mole of helium gas and 2 moles of helium gas. 1 mole of helium gas, and here also let us take same 2 moles of helium gas. Let us take. Okay. So now we have taken here 1 mole of helium gas, here 2 moles of helium gas we have taken. Let us remove the partition for both at the same time. Let them intermix. Now this 1 mole of helium gas is intermixing with argon gas completely by taking certain time. This 2 moles of helium gas also intermixing with this argon completely by taking certain time. That means let us allow them to go for intermixing completely. Let us allow them to go for intermixing completely. Let these two intermix with each other. Let these two intermix with each other. For intermixing completely, this will take certain time. This will take certain time. Now, do you feel time taken for intermixing of these two will be same or different? If you say different, which takes more time for complete diffusion, that you say. That means let these two intermix with each other. Remove this partition, let them intermix with each other. For that, it will take some time. This helium gas is taking certain time for complete intermixing. Here also remove partition. Let us allow this helium to intermix with the argon. For that, it will take some time. Do you think that both are going for intermixing by taking same time or different time? What do you feel? For intermixing, both helium gases, here this helium gas and this helium gas will consume same time or different time, different magnitude of time. What do you feel? Same magnitude of time they will take, or different magnitude of time they will take. You are saying that different magnitude of time. Sir, okay. It takes a certain time for intermixing. It takes certain time for intermixing. Sir, okay. Different time in the sense one is consuming higher magnitude of time, another is taking less time. Okay. Now out of these two, which takes more time for a diffusion, which takes more time for a complete diffusion, which takes more time for complete diffusion, do you think? Which takes more time for a complete diffusion, do you think? Which takes more time for a complete diffusion? That means both cases will take same time for different time, we said. Second is taking more time, you are saying. It is taking more time for complete diffusion. It takes less time for a complete diffusion. That means you think that this rate of diffusion, depending on what you see. Rate in the sense, rate of diffusion means velocity of diffusion. Otherwise, speed of diffusion. The speed of diffusion depends on which factors you see. That means, will they depend on number of moles? Will they depend on time taken? That means rate of diffusion. Rate means velocity. Velocity means what? Velocity means a certain thing happening per unit time. That is called velocity. Certain thing is happening per unit time. That is called velocity. Here, certain thing happening means these moles and these moles are mixing. That therefore, how do we define rate of diffusion? Shall we define rate of diffusion as a number of moles of gas diffused by time taken? Number of moles of gas diffused by time taken, shall we say? So rate of diffusion is called a number of moles of gas diffused by time taken. Like that we can say. Rate of diffusion is called a number of moles of gas diffused by time taken, we can say. Sir, okay. Now we will consider here rate of diffusion. In this case rate of diffusion is N1 by T1. Number of moles of gas is here, and the time taken is it takes certain time for intermixing. Then in this case, number 2, Number 2 will say rate of diffusion is equal to number of moles of gas diffused by time taken. Like this we can say. This number 2. Number 2 is here. Here for number 2, rate of diffusion is equal to number of moles of gas diffused by time taken. Like this we can say. Next, let us divide 1 by 2. Now we can say R1 by R2 is equal to R1 by R2 is equal to what we can say means N1 by T1 into T2 by N2. Like this we can say. So we can get R1 by R2 is equal to R1 by R2 is equal to N1 by N2 into T2 by T1. T2 by T1. This is called what means relative rates of diffusion. This is called relative rates of diffusion. Relative rates of diffusion. So relative rates of diffusion is called is nothing but this one. Shall we say now we will come for another idea, number of moles and volume. What is a relation that we will see. Now here we got an idea that R1 by R2 is equal to N1 by N2 into T2 by T1. We got an idea. Now let us consider Avogadro's law. Avogadro's law says that volume of gas is directly proportional to number of moles of gas. If we consider Avogadro's law, now in the place of number of moles, shall we consider volume of gas provided pressure and temperature remains constant? By keeping pressure and temperature constant, we can say Avogadro's law, volume of gas is directly proportional to number of moles. If we keep pressure is constant and temperature is constant, then we can say number of moles of gas is directly proportional to volume of gas. As per that, if we substitute Avogadro's law, then we can say in the place of number of moles, we can write volume of gas diffused. We can say volume of gas diffused. Then the formula becomes like this. In the place of number of moles of gas diffused, we can say volume of gas diffused, we can say. Next, now we will consider like this. We will consider one long tube, we will consider long narrow tube, we will consider. Here one end, it is one open end, it is one open end. Like this we will consider. Let us pass ammonia gas here. Ammonia gas let us pass. And let us pass here HCl gas. HCl gas. Okay. Now both gases are traveling. Ammonia gas is traveling in this direction. HCl gas is traveling in this direction. Now we can consider that molecular mass we will take. Molecular mass of ammonia we will take. Molecular mass of ammonia in the sense atomic mass of nitrogen plus 3 into atomic mass of hydrogen. It is called molecular mass of ammonia. Molecular mass of ammonia means atomic mass of nitrogen plus 3 times atomic mass of hydrogen. Atomic mass of nitrogen is 14 plus 3 into atomic mass of hydrogen is 1. So molecular mass of ammonia is 17 gram per mole. Sorry. So molecular mass is 17 gram per mole, that we can say. Sorry. Another point, molecular mass means we can say in terms of AMU, in the unit of AMU. Gram molecular mass means unit is gram. Sorry. Now molecular mass of ammonia is 17 AMU. It is nothing but mass of a molecule, mass of ammonia molecule. So mass of ammonia molecule is how much means 17 AMU. This AMU we can convert into gram by multiplying with 1.67 into 10 power minus 24 gram. Sorry. So mass of ammonia molecule is how much means 17 AMU. Mass of ammonia molecule. Mass of ammonia molecule is how much means 17 AMU we said. Now HCl will take, for HCl molecular mass in the sense for hydrogen atomic mass we will take, chlorine atomic mass we will take, we will add hydrogen atomic mass 1, chlorine atomic mass 35.5. So molecular mass is how much means 36.5. Therefore mass of HCl molecule. Mass of HCl molecule how much means 36.5 AMU. Mass of HCl molecule is how much means 36.5 AMU. Like that we said. So mass of HCl molecule we said. Now let us provide other conditions. Say here pressure of ammonia. Here pressure of ammonia. Let us keep same. Here temperature of ammonia. Here temperature of ammonia. Let us keep same. Here number of moles of ammonia gas taken. Here number of moles of HCl gas taken. Let us take same. All the conditions we will provide same. air pressure same, air temperature same, air number of moles same. Only difference is what means this mass of this molecule, mass of one molecule is 17 AMU, mass of one molecule is 36.5 AMU. That means mass of this molecule is low, mass of this molecule is high. That means in the mass, in the sense it is somewhat lean, it is somewhat stout, like that we can say. Now ammonia is traveling in this direction, HCl is traveling in this direction. They will meet at one point. They will meet, ammonia and HCl will meet at one point. Suppose this point or this point or this point. At certain point, they will meet. Now, do you think that both will meet with each other at one point? That point will be exactly center or close to HCl or closer to ammonia. Which do you think? Now, ammonia is traveling like this, HCl is traveling like this. At one point, they will meet with each other. That meeting point will be center of the tube or closer to HCl or closer to ammonia, or what do you think? In which point they will meet? In which point they will meet with each other? Which point? Near HCl. So you are saying that they will meet near HCl, you are saying. So near HCl means, suppose we will take this point. At this point, they meet with each other. Okay, they meet with each other at this point. That means you are saying that here you said near HCl they are meeting, like this you are saying. Now let us take distance traveled by ammonia. We will take distance traveled by ammonia is this much. It is the distance traveled by ammonia. Distance traveled by ammonia is this much. Distance traveled by HCl we will take. Distance traveled by HCl. Distance traveled by HCl is this. Distance traveled by HCl is this much. So, if you see, HCl is traveling less distance. HCl is traveling less distance. Ammonia is traveling more distance. Ammonia traveled more distance. HCl traveled less distance. Sorry, okay. Now we will see time taken for ammonia and time taken for HCl. That point we will see. Time taken by ammonia, time taken for HCl. That we will see. What do you think that time taken by ammonia for moving, time taken for HCl for moving? Do you think that they have taken same time or different time in order to meet, in order to come to this place? In order to come to this place, what do you feel? They have consumed same time. They have consumed same time in order to come here. In order to come here, or different time? In what way do you feel? That means ammonia takes certain time to reach this point. HCl takes certain time to reach this point. Do you think that they consumed different time to meet this place, or same magnitude of time? Okay, you are saying that they consumed same magnitude of time to reach this place. Sorry, okay, time taken is same. Okay, they have consumed same time, same magnitude of time to reach this place. You said same magnitude of time they have consumed. Sorry, okay. Now, shall we say rate of diffusion? Now we will say rate of diffusion. Rate of diffusion means velocity of diffusion, speed of diffusion, in what extent they have traveled, what extent they have moved. That is called a rate of diffusion. Now, rate of diffusion of ammonia, rate of diffusion of ammonia, that will take. Rate of diffusion of ammonia, rate of diffusion of ammonia, rate of diffusion of HCl. Do you feel that same or different? Rate of diffusion of ammonia and the rate of diffusion of HCl. Do you feel that value, that magnitude remains same or different? Rate of diffusion of ammonia, rate of diffusion of ammonia, rate of diffusion of HCl. Do they that value remain same or different? Rate of diffusion of ammonia and the rate of diffusion of HCl, will they be same or different? Rate of diffusion of ammonia, rate of diffusion of HCl, they are different. Rate of diffusion of ammonia, rate of diffusion of HCl is different. Then shall we say that rate of diffusion of ammonia is high, rate of diffusion of HCl is low, therefore ammonia traveled a larger distance HCl traveled less distance, shall we say? Rate of diffusion of ammonia is high, rate of diffusion of HCl is low, therefore ammonia has traveled more distance, HCl has traveled less distance, shall we say? Okay. Now, rate of diffusion of ammonia is more, therefore it has traveled more distance. It has traveled more distance. Rate of diffusion of HCl is less, therefore it has traveled less distance. So from this we can say that rate of diffusion we can say in terms of distance traveled. So rate of diffusion R1 by R2 is equal to distance traveled by first gas by distance traveled by second gas into time taken by second gas by time taken by first gas. Like this, we can say rate of diffusion. Relative rates of diffusion, we can say like this. Sir, okay. Next point we can say, here see that we came to an idea that R1 by R2 is equal to N1 by N2 into T2 by T1 or V1 by V2 into T2 by T1 or D1 by D2 into T2 by T1. Sir, okay. Next, see that here rate of diffusion of ammonia is high. Rate of diffusion of ammonia is high. See the molecular mass of ammonia, 70. Rate of diffusion of HCl is low. That's why it has traveled less distance. The rate of diffusion of HCl is less. That's why it traveled less distance. Rate of diffusion of ammonia is high. That's why it has traveled more distance by consuming same time for both. Both have consumed same time, but ammonia traveled larger distance. HCl has traveled a lesser distance because rate of diffusion is different. Rate of diffusion of ammonia is more. Rate of diffusion of HCl is less. Sorry, okay. Next, let us see rate of diffusion and molecular mass relation. Rate of diffusion and molecular mass relation, let us see. Rate of diffusion of ammonia and its molecular mass will see. Rate of diffusion of HCl and its molecular mass will see. Relation will see. Molecular mass of ammonia is less when compared to HCl. Molecular mass of ammonia is less when compared to HCl. Rate of diffusion of ammonia is more when compared to HCl. So, rate of diffusion high, molecular mass is low. Rate of diffusion low, molecular mass is high. So, what will be the relation between rate of diffusion and molecular mass? Will they be directly proportional? Will they be inversely proportional? Or will they be what do you say? Directly proportional or inversely proportional, or in what way? Inversely proportional. So rate of diffusion and molecular mass are inversely proportional to each other. So what Graham says? What Graham says that we'll see. Graham's law says that rate of diffusion is directly proportional to 1 by square root of molecular mass. Rate of diffusion is directly proportional to 1 by square root of molecular mass. So if we take this as first gas, let us take this as first gas. For first gas, let us give R1 is directly proportional to 1 by square root of molecular mass M1. Let us take this as second gas. For second gas, we will say that R2 is directly proportional to 1 by square root of molecular mass. Like this we have taken. Now we can come to an idea that R1 by R2 is equal to square root of M2 by M1. M2 by M1. Like this we can come an idea. So R1 by R2 is equal to square root of M2 by M1. Like this we can say. Next point we will see. Molecular mass and vapor density relation will see. Molecular mass is equal to 2 into vapor density. It is a relation. Molecular mass is equal to 2 into vapor density. Molecular mass is equal to 2 into vapor density. As per that, we will see R1 by R2 is equal to square root of M2 by M1. Now let us substitute this vapor density in the place of molecular mass. Then we will get a vapor density of second gas by vapor density of first gas square root. So R1 by R2 is equal to square root of M2 by M1, which is equal to square root of vapor density of second gas by vapor density of first gas. Like this we got. Next, Next, let us take here some gas. We will take here. We will take some gas. We'll take some gas. Suppose helium gas. Density of helium gas. Density of helium gas is helium. The helium gas is having certain density. Like this, we'll take. Next, here we will take some gas. Suppose we are taking helium gas. It is having some density. Here we will take some neon gas. Here we have taken some neon gas. Okay, like this, two vessels we have considered. Now let us go for another point. Density of helium gas is high. Density of helium gas is less. Like this, we'll take. Here pressure of helium gas. Here pressure of helium gas same. Here temperature of helium gas. Here temperature of helium gas same. Like this, we'll take. But how the density is there means different. How the density is there means different. Like that is there. Okay. Now let us remove this partition. Let us remove this partition. Let them intermix. Let us remove this partition. Let them intermix. Now after removal of partition, they are going for intermixing. Now, do you say that both intermixes by consuming same magnitude of time? Shall we say both intermixes completely by taking same magnitude of time? Shall we say? Can we say or not? Both intermixes by consuming same magnitude of time or different magnitude of time. What do you say? That means you are removing this partition, they are intermixing. You are removing the partition, they are intermixing. Both are intermixing with each other. Shall we say that both intermixes with each other by taking same magnitude of time or different? Okay. You are saying that different magnitude of time. So, which takes more time? Different in the sense one is taking a higher magnitude of time. Which takes a higher magnitude of time for complete intermixing. Which takes higher magnitude of time for complete intermixing means you are saying that the one student says that first one, which takes more time in the sense first one you are saying. First one takes more time for complete intermixing. Sir, okay, let us check this one. Now, density in the sense number of moles by volume. What is called density means number of moles by volume. Density is equal to number of moles mass by volume. Number of mass by volume, it is called a density. Mass by volume. The year we said pressure temperature same, we said even we will take volume also same. Volume also same. So we placed this volume is same, we said. Now mass, that means density is different means mass should be different because we considered volume is same. So mass should be different. Mass we will take in terms of moles. Mass we will take in terms of moles. So how the moles should be there means here number of moles should be high, here number of moles should be less. Like that should be there. Because density is equal to mass by volume. Density is equal to mass by volume. We said volume remains same. Volume remains same, we said. So mass should be different. Mass is nothing but moles. So number of moles is more, so density is more. Number of moles is less, so density is less. Now see, more number of molecules are there. Less number of molecules are there. More number of moles means more number of molecules. Less number of moles means less number of molecules. Because 1 mole is equal to Avogadro number of molecules. Here number of molecules are more. Here number of molecules are less. Here these molecules are intermixing with these. That means both gases are intermixing completely by taking certain time. Both gases are intermixing completely by taking certain time. Now think and say, here number of molecules more, here number of molecules less. So for intermixing completely, both will they consume same magnitude of time or different means you said different. Sir, okay. Which will consume more time for complete diffusion? Which takes more time for complete diffusion? Or will it consume more time for complete diffusion or will it consume more time for complete diffusion? Which takes more time for complete diffusion? First gas or second gas? Which takes more time for a complete diffusion? Which one takes? Do you think that first one? Do you think that first gas is taking more time for a complete diffusion? Sir, you are saying that first gas is taking more time for complete diffusion. So time consumed is here high. Time consumption is high for this. Time consumption is high for this one. Time consumption is less for this one. So that means now we will go for rate of diffusion. Rate of diffusion here, rate of diffusion here. We will see. It is taking more time. It is taking more time for diffusion. It takes more time for intermixing means how the rate of diffusion will be there. It takes less time for intermixing means how the rate of diffusion will be there. You see, where rate of diffusion will be high. Do you feel? It takes more time for complete diffusion. It takes less time for complete diffusion. So rate of diffusion will be high for which one do you feel? Rate of diffusion will be high for which one do you feel? Time consumption, you see, it takes more time for complete diffusion. It takes less time for complete diffusion. So rate of diffusion means velocity of diffusion. You are saying that this gas is take for this rate of diffusion high, for this rate of diffusion is low, then we can have an idea that rate of diffusion is low, density is high. So rate of diffusion and density are inversely proportional. Rate of diffusion is low, density is high. So rate of diffusion and density are inversely proportional. Rate of diffusion and density are inversely proportional. So we can say that here density of second gas by density of first gas, like this we can say. So R1 by R2, R1 by R2 is equal to so on. So R1 by R2 is equal to square root of M2 by M1, square root of vapor density of second gas by vapor density of first gas equal to square root of density of second gas by density of first gas. Like this we got an idea. Sir. So how the intermixing is there, that point we have got an idea. Okay. So relative rates of diffusion, form relative rates of diffusion, how to find that we came to know it. Sir, okay. Now let us take a vessel here. A vessel we are taking. Here partition is there. Here partition is there. Let us take helium gas here and neon gas is here. Neon gas here. Another vessel we will take. We are taking another vessel. Here let us take helium gas and neon gas. Neon gas will take. Sorry. So like this two gases we will take. Sorry, okay. Suppose we are considering here suppose argon gas. Here we will consider argon gas. Now this molecular mass is M1, this molecular mass is M2. Molecular mass is different because they are different gases. Here helium gas, here argon gas. So this molecular mass and this molecular mass are different. It is having some pressure, it is having some pressure. Let us think that they are having different pressures. We can take no. This pressure of this gas and pressure of this gas are different. Like this we can take. Then we will say temperature of this gas, temperature of this gas. Let them different. Temperature of helium gas, temperature of argon gas, let them different. Then let us make partition. Let us make partition. Here how the partition is there, we'll see. Here partition is like this. Here tiny hole is there. Here also partition is like this. Here tiny hole is there. This is what means tiny hole. Okay. Now in this tiny hole we will show the difference. We will show the difference. We will show the difference like this. We will show difference is there like this. That means area of this gap is different. Area of this gap is different. Here area of hole is high. Here area of hole is less. So like this is there. Now how the rate of diffusion will be there, that we have to see. How the rate of diffusion. Here rate of diffusion